Hello, everyone. My name is Fosu Emmanuel, and today I'll be giving a presentation over my research work over the past year. So over the past year, I've been looking at the oxidation of ethylene by group 7b of the complexes of the form LMO3. And I use DFT, or density functional theory, as the quantum mechanical model in performing this theoretical study. So as a computational and theoretical chemist, I am dedicated to applying state-of-the-art computational techniques in understanding processes of nature at fundamental scales of matter. So in quantum chemistry, we make good use of equations such as the Schrodinger equation, and after that, the data that we get, we use this data, or the energy values that we get, we use these energies to explain the reaction mechanisms and also dynamics of any physical property in question of chemical, biological, and also physical processes. Experimentalists then pick up these ideas and then apply them in biotechnology, nanotechnology, and drug design. Over the past years, oxidation reactions have shown considerable relevance, and one typical oxidation reaction, is the hydroxylation of olefins. So in here, we try to form vicinal diols from the addition of ethylene to osmium tetroxide. But the issue about this reaction, one, was with its mechanistic details. So initial proposals was that the olefinic moiety has across the OOSO functionality in a 3+2 manner to form a dioxylate before undergoing hydrolysis to form diols. However, due to the oxidation abilities of early transition metal also complexes, the Sharpless and his group proposed that the reaction rather goes to the 2+2 addition, where we form a metallar oxidane, which now serves as a precursor for the formation of the dioxylate. Over the past years, there have been several quantum works to study the reaction mechanisms of the addition of ethylene to osmium tetroxide. So in here, the red lines represent the 3+2 pathways, and the two black lines represent the 2+2 pathways. So from this energy profile, it is evident that the addition of ethylene to osmium tetroxide will proceed via the 3+2, because we are seeing low activation barriers for the 3+2 as compared to the 2+2. And also we are seeing negative reaction energies, telling us that the 3+2 reaction surface is quite spontaneous as compared to the formation of the metallar oxidane from the 2+2 surface. Now, from the mechanistic details, another issue about this reaction is with the several factors that demerit the use of osmium tetroxide. So factors such as its expensive nature, scarcity, toxicity, and a whole lot demerit the use of osmium tetroxide. So there's a need for researchers to look for other oxidants that can perform better than osmium tetroxide in oxygen transfer catalysis. So in here, so on my left, represent the computational details. So all modeling were done on the Spartan and Gaussian modeling programs. So for the equilibrium geometries or structures on the minima, they were run after minimizing the structures interactively by the cyber force field. And after running them at the DFT level, they are any degree of freedom, any frequency corresponding to any degree of freedom in that system had a real frequency, and this was different from the structures obtained at the saddle point. So the transition state obtained from the scans, dynamic constraint, and also the electron flow method, it could be seen that the reaction, the vibration corresponding to the reaction coordinate had an imaginary frequency. So in this work, I will explore the 3+2 pathway, that's pathway A, leading to the formation of the intermediate 1A, the dioxylate, through transition state TS1A, which can rearrange through TS2A to form 1B. I will also look at pathway B, which is the alternative 2+2 pathway, and also look at how oxygens can serve as precursors for the formation of epoxides. I also look at pathway C, where we get to see the direct addition of the oxoligand to the olefinic moiety. So my results in discussion, the first one looks at the interaction between the frontier molecular orbitals. So for all anionic computer structures, that's the perrhenate, pertechnetate, and the permanganate complexes, it was seen that the flow of electrons rather moved from the oxo complex into the LUMO of the ethylene, which was quite different from what we saw in the analogs of these group 7b oxo complexes, where rather the oxo, the HOMO of the ethylene, rather couples with the LUMO of the oxo complexes. This can be accounted for by the high electronic density on the anionic complexes due to their negative charges. So these are the energy profiles to explain the energetics here. So the black lines represent the uranium catalyzed pathway, the red lines represent the T-save, and the blue represents the MN. So in here, it is evident that for you to form diodes, the MnO4 is the, how do you call it, is the best or is the most kinetically and thermodynamically favored pathway, because we are seeing the lowest activation barrier, which is a kinetic property, and also seeing the lowest reaction energy, which is a thermodynamic property. In all cases, the 3+2 was favored over the 2+2. However, the formation of epoxides was not possible for the Mn pathway, and in the TC and the RE pathway, the formation of epoxides was possible through the 2+2 pathway. Was not possible in all cases. So this rather tells us that if you are having your permanganate, your perrhenate, and your pertechnetate complexes, they would exclusively yield diols. However, this was different in all cases, in the analog substituted cases. So for MnO3F, it could be clearly seen that there was no way we could form diols, but however, the 2+1 pathway was quite feasible, indicating that for MnO3F, it would oxidize olefins exclusively, whereas the TCO3F and ReO3F would give racemic mixtures of epoxides and diols. However, their energetics does not favor their formation, and at high temperatures, they are likely to form. So in conclusion, it can be said that still Sharpless argument on the mechanistic details does not apply for these types of oxidation, and the addition for these types of reaction rather goes to the 3+2 pathway. And for the direct 2+1 pathway, it's only feasible for the MnO3L. In all cases, the catalyzed pathway or the structures were unstable on the singlet, were stable on the singlet surface, except for the formation of the dioxylate from the MnO3F catalyzed pathway. That's the dioxomangana 2,5-dioxylone intermediate. And in all cases, as said earlier, the HOMO of the ethylene couples with the LUMO of the complex in all cases, except in the anionic cases. Thank you. The further details on this work can be obtained from the paper that is attached at the first page. Also, if you have, I'll be willing to answer questions on this presentation. Thank you.